Testing, testing, testing. This is a test of the broadcasting system. All right, so we've looked at all of our basic stats, and we have our measures of central tendency to tell us where the midpoint of the distribution is. And then we have our measures of dispersion telling us how far out our system goes. Now, when the data is believed to be approximately bell-shaped, a symmetrical normal curve, so when I have my data that kind of looks like this, here's my little bell curve, here's my mean, my median, my mode. Whenever the data is put together like this, we can employ something that's called the empirical rule. And the empirical rule really tells us about how much of the data falls between certain things. So let me let's draw this a little bit bigger here. So here's my normal distribution. Here's my mean, right in the middle. And once again, this is also the mean in the mode. So this is X bar if we're talking a sample. This is, just grab the edge of my thing. It's mu if it's the population. So the empirical rule tells us the percentage of data that we have within specified numbers of standard deviations. So if I sit here and I go, and let's choose a different color. If I go one standard deviation away from the mean, so if it was the sample, it'd be 1s. If it's the population, it's 1 sigma on either side. So plus or minus 1 standard deviation, that's going to contain 68% of all of the data points. So in a normal distribution, the data will cluster around the middle. And then if I go out two standard deviations, so I had another sigma here, another sigma here, or if I'm talking the sample, an S here or here. So that's going to be plus or minus 2 standard deviations is going to be 95% all the data. And then if I go out one more, if I hit that third standard deviation, so sigma here, plus or minus 3, let's get that out of the way. Okay, maybe not. Plus or minus 3 standard deviations is going to be 99.7% of the data. So almost all of the data in a normal distribution is going to fall within 3 standard deviations of the mean. And so this is kind of a powerful thing. This helps us identify outliers, because if 99.7% of the data is going to be within 3 standard deviations of the mean, anything outside of that is obviously going to be an absurd or a strange or non-normal value. And you'll do this a lot when you're looking at, say like stock prices and stuff, and you've got one stock that's like, hey, the return over this past quarter is like 4-5 standard deviations from the mean. It's like, well, that's a fantastic performing stock because it's so far out of the mean. Now, actually, if you look at this too, if you ever work in a company that's a manufacturing environment, or you become a CMA yourself, which is a certified manufacturing accountant, so both finance and accountants do that, you'll run into something called Six Sigma, which is a statistical method of ensuring zero defects in manufacturing. That's actually where this comes from, because here's 1 sigma, 2, 3, 4, 5, and 6. So 6 sigmas across the distribution encapsulates all of the data. All right, so that's our empirical rule, but we do have a special case when we're looking at the empirical rule, and that is something that's called the standard normal distribution. So whenever we talk about standard within a statistical context, we are talking about something that is going to be standardized, so we can compare it against each other. So the standard normal distribution is a normal distribution. And it's a theoretical distribution, but it's used for comparing 2 different data sets and 2 different numbers together. And so you're calculating the probability of individual observations off that. So the standard normal curve, the mean, the median, and the mode are all 0. And the standard deviation is 1. So we have this normal curve that's going to be sitting right in the middle of everything. So if I look at it, my standard normal curve looks like this. Here's at 0. So within 3 standard deviations of the mean, it's still like all of the data, but now those standard deviations are written as just a single number. Now, what do we use this for? We use this for something that's called the z-score. And what the z-score does is, it's also known as the standard score. It's a statistical measure that tells you how far you are from the mean in a data set, and all in terms of standard deviation. So this is great when you're comparing, when you need to compare things across like time. So typically we'll sit there and final project, somebody's like, well, I want to show that LeBron James is a better basketball player than Michael Jordan. And they will come and say, well, he's better because, you know, he averaged this many more points than Michael Jordan did. And you have to sit there and go, wait a second. They played at two different times. You can't really directly compare them to each other. What you kind of got to do is you've got to standardize this so you're comparing like to like. And the z-score is a good way to do that because you can sit there and look at one player and how he compares to the average of the league of his day versus another player and how they compare against the league of their day. And you can sit there and go, well, yeah, you know, LeBron James scored a lot of points, but he's only 2 standard deviations above the mean compared to the rest of the players his day, where like Michael Jordan may have been like 3. And so that way you can compare things together. And so it really allows you to see how far or from the mean things are and compare them across different things. So it's a really handy thing to be able to do because you are measuring standard deviations. Something else that you would use this for, that just another example, would be that normalizing and standardizing data. So let's say you have 10, you're getting evaluated on something, and you've got 3 evaluators for each group, and they're evaluating you on a 1 to 5 scale. Well, it turns out most people don't actually use the entire 1 to 5 scale. They'll cluster everything 3 to 5. And then you'll throw somebody like me in who does use all the way from 1 to 5. It's kind of unfair for the person being evaluated, because if I'm starting at 1 and everybody else is starting at 3, my scores are in general going to be lower than the other reviewers. So what they do is they use a standardized normal curve. They look at all of your ratings and they sit there and go, okay, well, this rating is this many standard deviations from the mean. And then you can directly compare that with other ones. And z-scores are also used to identify outliers, because anything that has a z-score greater than or less than 3 would be an outlier, because that's outside of the bounds of the set, because plus or minus 3 on standard deviation is what gives you your 99.7% of the data. So how do we calculate out a z-score? A z-score is really easy, depending on whether you're dealing with a sample or the mean. So the z-score, if I'm using sample terminology, would be x, which is whatever point that you're looking at, minus the mean of the data set, and then I will divide that by the standard deviation. And then if I was using the nomenclature for the population, this would be x minus mu divided by sigma. So, I mean, they both mean the same thing. So let's say that we went through your class and we calculated things out and went, okay, the average height of our class is 5 foot 8 inches. So that would be x bar. So that is 68 inches tall. And the standard deviation of our population was 2 inches. So we can sit there and, we can look at this in terms of z-score. So let's say that, we'll throw myself into the mix. I'm 6 foot tall. 6 by 12 is 72. So my x value for my height is 72 inches. So if I go and I calculate out my z-score for this, I've got my z-score would be my height, which is 72, and then I'm going to subtract from that 68, and then I will divide it by the standard deviation of 2. So 72 minus 68 is positive 4 divided by 2. That would give me a z-score of 2, which means that I am 2 standard deviations above the mean. All right, and so what happens if you're shorter than that, 5 foot 8? So we'll use the other Dr. Camp here, and so she is 5'6". So x would be 66 inches. Actually, she's 5'4". So let's make her shorter then. So she's 5'4", so that's 64 inches. So I go and do my z-score. So z is equal to 64 minus 68 divided by 2. So that's going to give me a -4. -4 divided by 2 is going to give me a z-score of -2. So she would be 2 standard deviations below the mean. And so the z-score, the important thing to remember there, the reason it's set up the way it is, plus or minus, will tell you, positive standard deviations or negative standard deviations. And once again, this is pretty cool with outliers, because if we have a normally distributed data, if it's greater than 3 or less than -3, we can sit there and go, that's an outlier based on all the other data that we have. So with the whole empirical rule and z-scores, I expect you to be able to calculate these out. I also expect you to be able to kind of look at something. And so if I say that, hey, our average is 68 inches, our standard deviation is 2, well, what range of heights would give us 68%? So that's 1 standard deviation. So if I go 1 down, that'd be 66 inches. And then if I go 1 up, it's 70 inches. So if I was looking at the height of the class, 68% of the people would be between 68 and 70. What if I wanted to know, 99.7? So once again, I look at this and the average is 68. 3 times the standard deviation would be 6. So 68 minus 6 is 62 inches. And then on the other end, 68 plus 6 would be 74 inches. So 99.7% of the students will be between 62 and 74 inches. And of course, I have no idea what the average height in the class is. These are just all made up numbers. But that's the empirical rule. And this is going to become important as we start doing analysis and we kind of look at things and we're like, wow, that's really far outside of what's going on. That's kind of weird. All right. With that, that's the end of the empirical rule. And I will see you guys in the next video.